Alright, today we're going to be looking at what energy is, and we're going to be looking at the definition for it, the law of conservation of energy, different energy transformation parts, so potential to kinetic energy, and then today we're going to focus on the potential energy equation, and then tomorrow we'll focus on the kinetic energy equation. So first off, we need to know what energy is. So energy is the ability to do work. Okay, and work just means you're applying a force to that object. You could also say it's the ability to apply a force on an object and the object moves in the same direction. When you're looking at energy and we're trying to figure out what has energy and what doesn't have energy, anything that causes a change must have energy. Alright, so when I was writing, my pen had kinetic energy because I was moving with my hand. I was applying a force to it, so it had kinetic energy to it. Now I'm holding it still, so it has potential energy to it. Then when I go back and start writing, I'm going to turn it back into kinetic energy. Now when you're doing your energy notes and you're going through all the different types of potential and kinetic energy, you're going to need to know what the SI unit is going to be. Well, your SI unit is going to be the same for all energies. So it doesn't matter which energy you were looking at, they're going to have the same SI unit to them, and that SI unit is going to be joules, or a capital J. And then we need to know the equivalency of it, and that's going to be 1 joule equals 1 kilogram times meter squared per second squared. So this portion here looks very similar to what you looked at to be a Newton, or what your unit was for momentum. Momentum didn't have either the squaring. A Newton only squared the seconds, or the time. And now for a joule, the meter and the seconds are both squared. That's the difference between them, is where you're squaring and where you're not squaring. So that's why you have to make sure that you pay attention to where the squares are to know if it's a Newton, momentum, or a joule. Okay, are there squares? Are there not squares? If they're squares, what's going to be squared? That will tell you what that equivalency is going to be. Now, when you're looking at these different types of energy, they're going to go through different energy transformations to go from one energy to another energy. So, therefore, they are going to follow the law of conservation of energy. So just like there's the law of conservation of mass, there's the law of conservation of momentum, there's going to be the law of conservation of energy that kind of take on the same idea for each one, because you're looking at this word conservation. So it's going to state that energy is not created nor destroyed. So it's just saying that it's going to change from one form to another. So potential to kinetic, from kinetic back to potential, a specific type of kinetic energy into potential, or vice versa. So you're not creating or destroying, you're just changing it from one form to another. And in the end, the overall amounts will remain the same. Okay, so even though it's changing forms, the overall amount remains the same. Now, when you're looking at this law of conservation of energy, it's also known as the first law of thermodynamics. Alright, and thermodynamics is, there's two laws associated with it, and it just is telling how energy is going to be moving. So the first law, it states essentially the same thing as saying that energy is not created nor destroyed. It's just going to change from one form to another. They just use a couple different words. So therefore, the law of conservation of energy and the first law of thermodynamics are sometimes used interchangeably. Or if they say, what's another way to say the law of conservation of energy? It's going to be the first law of thermodynamics. And we'll talk about this first law of thermodynamics more when we get to chapter 14. Okay, we'll see what this first law says with a couple extra words, and we'll also talk about the second law of thermodynamics. Now we're looking at energy. Sometimes you have lost energy from the system. So for you to show or prove this law of conservation of energy, you would have to encapsulate that system so that you can know exactly how much energy you started with and how much you ended with. So it's the same at the beginning and at the end. But that's very hard to do sometimes in that system. And when you're looking at the ways that you can lose that energy, it could be in the form of heat, sound, or vibrations. So if you're looking at this, a lawnmower is a really good example. Okay, you put gasoline into your lawnmower that has chemical potential energy. You start the lawnmower through the whole combustion process. You turn it into kinetic energy. So you can cut your grass. You spin in the blade, it cuts the grass there. Well, what's happening in the engine itself? Well, you get heat to be produced because of the friction within the system itself is causing vibrations. So these vibrations cause heat to be produced. So it warms up. That's why if you touch the engine at the end of mowing your grass, it's hot. Sound. You can hear it. When you turn your lawnmower on, you hear the lawnmower running. Or if somebody is mowing their grass next door, you hear them mowing their grass next door because of the sound. You could also think about this as a hairdryer. Okay, when you turn your hairdryer on, you have within the hairdryer itself vibrations occurring, which causes heat to be produced. That also is heating up those coils that causes your hair to dry because the fan's blowing it, and it's sound. You can hear somebody when they're using a hairdryer. So when you're looking at this, sometimes you have lost energy from the system. It's just because you can't encapsulate that system to keep it within there. It's going to naturally go out. Okay, so a lawnmower or drying your hair are two examples of that. Now, if you're a person that is a roller coaster enthusiast, you are going to want potential and kinetic energy. Alright, so when you're looking at roller coasters, what's going to propel them? Okay, what keeps them going throughout the entire thing is going to be gravitational potential energy, kinetic energy, and heat. Again, that heat is because of that friction between the roller coaster and the track that it's on. When you're looking at how does the roller coaster stay on the track, well, it's held on the track by friction. Okay, friction, so you'll see friction being used a lot here. Friction, again, that's what's causing the heat there. And you have track couplings. Alright, so that's what's gripping the roller coaster to the track. So if the track is a pipe, the coupling goes around it to hold it onto the track itself. Now, as it's going through a path, so if we have a roller coaster going and it goes a loop-to-loop here and then goes to the next. Alright, and here's a little car with a little people hanging out there. Alright, and it takes its path down and around to wherever it keeps on going to. They want to know what's happening to the gravitational potential energy and the kinetic energy. Well, at the top here, you're going to have gravitational potential energy. They're not moving, so there's no kinetic energy. Okay, so right now, since they're not moving, your GPE is high. Okay, but your kinetic energy is 0. Alright, because we're pretending it's at the top of the hill, it hasn't been released yet, it's just sitting there and it's going to be 0. Now, once it goes over the hill, starts making its way down, right before it hits that loop-de-loop here, you're going to have low GPE, but high kinetic energy. You're going to be going super fast on here, so you're going to have high kinetic energy. Then you go around this loop, and then what happens at the top of the loop? You kind of start to slow down a little bit, even though you don't realize it. So, and then you start to accelerate back down. So at the top of this loop here, you're going to have high GPE and low KE, okay? Because GPE is based off of how high you are off the ground. So the higher you're off the ground, the higher GPE is going to be. The closer you are to the ground, the lower your GPE is going to be. And you see, as one goes up, the other one goes down. So this one was high, then it went low, this became high. Comes around, GPE is now high, and kinetic energy is low. And it will keep on going through the highs and lows to get to the end of the roller coaster. And the roller coaster is designed in such a way to cause those different highs and lows and make you feel like your acceleration by those loops and curves that you keep going around. Then you get to the end, and you throw the brakes on to stop you. Now, you could also say, if you have a person, okay, and there's my person's foot kicking a ball, so here's the ball, whatever ball you want it to be, alright, and it's going on its path. This is the grassy area here. But when it's at the top of its arc path here, you're going to have high GPE, low KE. Then, right before it hits the ground, you're going to have low GPE and high KE. Alright, so you're going to have those ups and downs. As one goes up, the other one's going to go down, and vice versa. So therefore, that's how you have roller coasters accelerating through. That's how you feel the different kind of forces being applied to you there. That's because of those highs and lows and curves here. So if you're ever asked to mark where your GPE and KE are high and low, we'll look for where the top of the path is. That's going to be GPE is high. When it's right before it hits the ground, or the closest to the ground, because here was close to the ground, then you're going to be looking at your kinetic energy being high there. Okay? So, that's the notes of what energy is. Now we're going to go over how to calculate potential energy, or sometimes they say it's gravitational potential energy. So you're going to need your formula sheet, just like normal. We're filling out our formula sheet here. Alright, and on our formula sheet, we're going to be looking at potential energy, or you can say we're just going to put in parentheses GPE. Okay, sometimes they just say potential energy, sometimes they say gravitational potential energy. That's the same thing, just a different term used there. Alright, now, when you are looking at this equation, you're going to have 4 variables now. So, GPE equals mass times gravity times height. Mass equals GPE divided by gravity times height. Gravity equals GPE divided by mass times height. And height equals GPE divided by mass times gravity. Alright? Also, it looks difficult, but really isn't difficult. Alright, so our GPE is our potential energy. And that's in joules. Our mass is m, which is in kilograms. Our g is gravity, which is in meters per second squared. And our h is height, and that's in meters. Now, you're going to want to make a side note somewhere. 1 joule equals 1 kilogram times meter squared per second squared. Alright, so that way you have it on there. Just like we put a Newton on here, you're going to put a joule on here. You can put it at the end here, you can put it over here, put it somewhere, so you know what a joule is going to be equivalent to. Alright, now, if we're on Earth, we have to remember gravity is up here, 9.8. Alright, so if they don't give you the number, you have to remember you're on Earth. If you can't remember you're on Earth, we got to work on that. Okay, you have to remember you're on Earth, and it's going to be 9.8. Alright, so we're going to do a few examples, and I'll do a couple questions off your worksheet also so that you can see what is occurring there. Okay, so I'm going to be looking at examples off of page 446. Okay, so we're on page 446, and we're going to look at number 1, letter A. So we're going to write our variables, GPE, M, G, and H. Okay, so it says calculate the gravitational potential energy of the following. We're just going to do letter A here for number 1. A 1,200 kilogram car at the top of a hill that is 42 meters high. Alright, so total is 1,200 kilograms. So we know that's mass. Total is 42 meters high. That's our height. We're on Earth. What is gravity on Earth? 9.8 meters per second squared. Okay, so they didn't tell us, but they know we know we're on Earth. Hopefully we know we're on Earth. Okay, so we're going to be solving for our potential energy. So mgh 1200 times 9.8 times 42. Now you're going to see you get a really big answer. It doesn't mean you're wrong. It's just because your numbers are high. So 1200 times 9.8 times 42 would give you 493,920 joules. Okay, so when you start looking at energies, you're going to get some bigger numbers. That doesn't mean you've done anything wrong. It's just what the numbers come out to be. Okay, so we're going to look at number 2. Go ahead and list our variables here. So number 2 says a science student holds a 55-gram egg out the window. Just before the student releases the egg has 8 joules of gravitational potential energy with respect to the ground. How high is the student's arm above the ground in meters? Alright, so we have 55 grams. That's going to be our mass. Then we have 8 joules. That's our energy. We're on Earth, so gravity is 9.8. Now, it tells you to make sure you convert your mass from grams to kilograms before you solve. So in this case, it's going to come out to be 0.055 kilograms. I moved that decimal 3 times to the left there. And now I'm going to solve for height. So, GPE divided by mg, 8 divided by 0.055 times 9.8. So we're going to carry that 8 over. So 0.55 times 9.8 would give us 0.539 on the bottom. 8 divided by that would give us 14.84. Okay, you notice you multiply the bottom first, jot that number down, and then take your top divided by that bottom number. That will give you the answers. If you forget to do that and put that on top first, you're going to get some crazy answer. Okay, you're going to multiply the bottom first, jot it down, and then take your top divided by your bottom to get your answer. Okay, number 3. A diver has 3,400 joules of gravitational potential energy after climbing onto a diving platform that is 6 meters above the water. What is the diver's mass in kilograms? Alright, so we list, and it gave us 3,400 joules, so that is our energy. Told us 6 meters, that's our height. We're on Earth, so gravity is 9.8. So we're solving for mass. So GP divided by GH. So 3,400 divided by 9.8 times 6. So we're going to carry that 3,400 over. So we'll get 58.8 on the bottom. We're going to take 3,400 divided by 58.8 to give us 57.82 kilograms. Okay, so again, I multiplied my bottom first, wrote that number down, and then took the top divided by the bottom to give me my answer. Okay, if you forget to do it, you're going to get some answer that doesn't make any sense at all. Okay, so those are the examples we're going to do off of page 446 there. Now, your worksheet. Okay, I always do some examples off your worksheet there. So we'll do some examples on that